All right, here at the Academy for Allied Health Biomedical Sciences, we're going to get into thermodynamics. Now, I'm probably going to play with these a little bit more for next year's class, but they'll work for us at this point. I really don't like the way Chapter 9's heat and Chapter 10 thermodynamics are put together. It really should just be one whole chapter because it's really done in a mess, in my opinion. Too many things overlap, and it overlaps with what we know in chemistry. So I find it a bit more confusing than it should be. I will try to work out the confusion that I've seen. Hopefully it will keep you on a straight path, but always email me with any questions. There's three sections that actually exist in this chapter, and we've kind of already talked about two of them. The first section talks about heat and work, a relationship between them. We have already talked about that, but not to the extent we're going to here. However, the other two really should be talked about ahead of this, and I've already mentioned it when we talked about heat, and that is the first and second law of thermodynamics and how they apply. It's really the whole thermodynamics piece, without just looking at heat, the whole thing has to really work together. So again, I do not like the way this is brought out. If you remember the in-class POGL work we were doing on thermodynamics and on heat, that has much more of a forward process that's much easier to understand than the way the book works this out. But you know what? Let me get these pieces out here and we'll work it through when we get into class. Okay, so what we're going to do here is we're going to recognize, look how long this first topic is. Recognize the system can absorb or release energy as heat in order for work to be done or by the system, and that work done on or by a system can result in the transfer of energy as heat. That's an awful lot to say. It's really just taking a look at what thermodynamics is, which really is the idea that they're trying to push is physics and the development of the heat engine, which has really become the process that we use for everything. The heat engine runs our cars, it runs our refrigerators, it runs our air conditioners, it provides us with electricity. It's where the big electric power plants, those things use big heat engines and turbines. We use the idea of the heat engine has become the crux for nuclear reactors, all that kind of thing. And so it really actually, this whole area of thermodynamics has a very important part because even today, it is the big perspective in how we were able to gain power. We put these heat engines everywhere. We use them for generators of electricity, and we literally would not be as advanced as we are. It is probably the single largest advancement of the last 100 years, 150 years, was the development of the heat engine because it allowed for industry and it got us into cars that allowed us to cut down on how far we have to travel. And then, of course, we've now used the heat energy to create airplanes and all that kind of thing. So, and we're even using it, well, we're not using heat energy for a rocket. Notice that's different technology. But anyway, this stuff becomes important. So this takes a paragraph to really tell you that what we're looking at from our standpoint as physics in our class, we're going to look at the system and the surroundings, and we're going to look at how you can take a system and have it do work on the surroundings or have the surroundings do work on the system to get things accomplished. That's really what you're looking at. You're also, of course, what does that mean? That means we, of course, have to compute the amount of work done in the thermodynamic process. And we have to distinguish between three types of processes that they want us to look at. The first is isovolumetric, the second is isothermal, the last is adiabatic. Now, I will say that there are more thermodynamic processes than these three, but these three are the chief ones that we use throughout modern life today. So that's why they become the three that you need to distinguish from. I also want you to understand that in all three cases, what your book doesn't tell you is that all of these involve what we call an isobaric process. And you're going to see that when I come up with some notes, because they actually put that in their notes. Isobaric, bar, of course, is used for pressure, right? Remember the millibar and the bar when I had you in chemistry and we were doing conversions for units of pressure? Well, isobaric means no change in pressure. And that's actually how these three processes are able to get work done. We'll see how this comes, all right? So just keep that in mind as we go through these. So let's talk about what thermodynamics is. Thermodynamics is the study of the properties of energy, specifically thermal energy, okay, and how it has a central role. That's what we're looking at right now, okay? So when we talk about heat work, we're going to talk about internal energy. We're going to go past now this aspect of the idea that everything has internal energy. Remember, I've told you before, there's no such thing as cold. There's no cold because even your inner body, even the molecules inside your body, they're always moving around. So everything is moving. Molecules always move. So it always has an internal energy. Okay? So what you say is no one has their own heat or their own work. What they really have is internal energy. So you want to simplify our terms and separate our terms out. Heat is something that goes into or out of a system, which is how energy gets transferred. But what heat will do is heat doesn't become something you have. It is used to change your internal energy. Okay? A little bit more confusing. Does it mean that there's no such thing as heat? No, there's heat. But it's internal energy that we're really concerned about. The system is, of course, what you're studying. It's what you're going to isolate. We want to isolate. In order for us to do our physics work and concentrating and get compute work and compute changes in internal energy or compute heat, we need to be able to make a system which is physically removed from the rest of the universe so we can study it. And of course, that means you have a system and you have an environment. In chemistry, we called it the system and the surroundings. Here we call it the system and the environment. And the environment will affect the behavior of the system. It's the universe, really. Okay? So, how do we make this work? In a thermodynamic system, work is defined in terms of pressure and volume change. So, this is work. As you can see, remember, work is force times distance, which you guys have to remind yourselves, and you should start taking apart in your head. Force is what? Mass times acceleration, correct? Okay, so if we're talking about a force of an object, and we're worried about the work that it's going to do here on this planet, what ends up with that force? That force usually becomes the weight of the object, which is mg. See how these things tie together? What does that mean? That means I've always got to keep my head thinking about those things, don't I? Yes, that's what it means. Okay, so it's force times distance. Now, force times distance can also be area over area, which means force over area can equal to area times distance. And remember from Archimedes, what's force over area? Force over area is pressure. Therefore, that could also mean, there you have, pressure is change of volume. Okay? Force over area is pressure. Area times distance is volume, right? So therefore, work is pressure times the volume change. Now, the assumption for this to work and thermodynamics must be that P, pressure, is constant. So what we're going to be concentrating on in our look at thermodynamics here in physics is isobaric processes only. Pressure is not changing. We'll try something out along these lines in our lab. Okay, so here we have isobaric, right? Which means we're going to be changing the piston from A to P or from P to A, depending. Okay, so what does this mean? If the gas expands, it means it goes from P to A. Then delta V is positive, and the work done by the gas on the piston is positive. If, however, we compress the gas and we go from A to P, then delta V becomes negative, and the work done on the gas on the piston is negative. Okay, so really what happens is the piston does work on the gas. It's the opposite. Okay, so for our purposes, for our system, if our system does positive work, that means that it's doing work to something. If we end up calculating and get negative work, that means work is being done on the system. This is important. You have tended throughout some of these to flub the signs. We've got to be very mindful of signs here and be very careful. Okay, so take a step back, rerun this, and run this through your head so you get that idea in, please. It will mean much more for you when you actually do the work. Now let's take a look at work in the first law of thermodynamics. Okay. The first law of thermodynamics talks about how things get done. That means that you've got to have a change in volume. If you notice in this graph, we've gone from initial to final. Okay. So, question, is work done by the system positive or negative? Okay. Well, the volume has expanded, which means final volume is greater than minus the initial is greater than 0. So the gas does work in its environment and gives energy away. So work done by the system is considered negative. Okay? Is the heat positive, negative, or 0 in this change? Okay? Since pressure is inversely proportional to volume, that means nRT is not changed during the transition, so Q equals 0. This is an example of an isothermic process where Q does not change. This is a little confusing. I actually have a better one coming up. Okay? Again, the first law of thermodynamics. If you notice, I can create a whole bunch of little squares. Okay? This is how we derive this P delta V and how you can understand how work gets done here. Okay? So, the magnitude of the work is equal to the area under the curve of this nice pressure versus volume graph. Okay? So that's why work is pressure P delta V. Okay? All I'm doing there is demonstrating how we derive the idea pressure times the change in volume is work. Okay? All right, so here come our processes. The isovolumetric process is a thermodynamic process that takes place at constant volume, which means no work is done by or on the system. The isothermal process is a thermodynamic process that takes place at a constant temperature. I'll give you some examples of all of these because that's the thing that I noticed was missing. And the adiabatic process is a thermodynamic process in which no energy is transferred to or from the system as heat. So Q will equal 0, which is what I was just talking about before. Okay, so that's 3 different types of thermodynamic processes. These are the 3 chief ones we want to look at. And these 3 are actually used for heat engines, refrigerators, air conditioners, etc. All right, how do they interact and what does this mean? Because one of the things I've noticed is your book is great about talking that and saying that, but then when you guys go to try to do the problems, there's very little to help you determine whether it's isovolumetric, isothermal, or adiabatic. Okay? So let's look at this first thermodynamic process, also called isochoric, known as isovolumetric. Notice when it's isovolumetric, so what do I want to do first? I want to read my problem. If my problem tells me I have an isovolumetric process, then that means work is going to be 0 and delta U will equal Q. Remember that equation we did with heat. W equals, or was it? No, delta U equals Q plus W, correct? Okay, so we're going to use that. So first law of thermodynamics for an isovolumetric process, change in internal energy equals the heat. Okay, so volume is kept constant. No work is done on or by the gas. And the first law of thermodynamics tells us that the change of internal energy must equal the heat gained or lost. Okay, in an isovolumetric process. So that's the equation. Q equals delta U, change in internal energy. All right. Here's the next one, isothermal. In an isothermal, we keep temperature constant. Therefore, this happens in what are known as, remember we were talking about this, isobaric, pressure is kept constant, so temperature can be kept constant. Work can be done by the gas or on the gas. The first law of thermodynamics says that the internal energy must equal 0. So that means if we put heat into the system, it's going in at a rate that is equal to the heat going out. So heat is going in and out of the system so that the temperature doesn't change. Therefore, heat equals work. Q equals W. Okay, so where is the work? Where is the heat? The heat isn't lost, as in it just doesn't just disappear. The heat is utilized for work as opposed to utilizing it to change the temperature of the system. All right, that's a little bit different than what we've been doing. Now, in those cases, what we usually like is, one of the better examples of that is the internal combustion engine actually does this, where we try to keep it isothermal. That's why we use a radiator and antifreeze to keep it from happening, because even though we try to do that so that the heat really gets used to move the car and run the engine and all that, unfortunately what really ends up happening is these engines do so where there's always excess heat. There's a lot of excess heat. So we try to keep things isothermal by utilizing antifreeze, utilizing a radiator, utilizing a fan. We also try to do the same thing for computers. There's fans for the computers. Why? Because we try to keep those components isothermal. It's one of the problems with the lithium-ion batteries. We want to keep it isothermal. We don't. We end up burning our legs when we try to put a laptop on our lap, which is funny how that's how the name laptop got made, right? Remember I talked about that. Okay, the third thermodynamic process is called adiabatic. Adiabatic is where you're compressing or expanding the gas in an insulated cylinder, so Q equals 0. When you do that, it has to be done fast enough so that you end up with no heat flow. That's one of the issues. Okay? First law of thermodynamics then says that the change of internal energy has to equal the work. So you get that, where Q is 0. Now, adiabatic processes are terribly tough to do. Usually we try to do them in, that's an example of refrigerators and air conditioners. Unfortunately, it doesn't work the way we want to. It's not perfect. These processes are ideal. Okay, so remember, they don't always work all the time, but they do set up our ideal processes. All right, so that's our first section. Thank you very much for listening, and we're going to move on into the first law of thermodynamics, which we kind of already talked about here. We'll expand on that a little bit more, and we'll do the second law of thermodynamics. Both of these will bring home the idea of the heat engine, the internal combustion engine, and the cyclic process. All right, see you in a bit.